Okay. Where are we at? Okay, cool. So I'm really bummed about this because I did like 3 hours plus of streaming where I didn't have I didn't have this display going. And so anyone whose problem I worked on, I apologize if you see this. Super lame. Oh, here's myself talking out loud. That's great. Okay. So let me know when you get in the chat if you can see everything. All right, here we have a question. It says, there is a camera on a tower 40 meters above the road. And so for the sake of this making sense, we're going to say that the tower is like directly above the road, like you're driving underneath the Eiffel Tower or something. Otherwise, this doesn't make sense to model it this way. So our tower, let's see if I can draw a nice line here, is 40 meters tall. Okay, and then from the base, actually, let me just read this. There's a camera on a tower 40 meters above the road. The camera rotates in order to film the arrival of a car. The car is moving along the road directly toward the tower at a constant speed of 10 meters per second. How fast is the camera rotating in radians per second? Okay, so at the instant the car is 96 meters from the base of the tower. So we want to know the moment that the car, let's say the car is here, here's a car traveling in this direction at actually traveling in this direction. I'm going to call this negative 10 meters per second. Okay, that's the speed of the car. The moment the car gets to this point, which is 96 meters from the base of the tower, which is here, okay, we want to know how fast is this angle theta changing, okay, in radians per second. So there's two things going on here. We have like the fixed rigid triangle, 40 and 96 being the legs, and then we have the rates of change with respect to time of the angle and the linear velocity of the car, right? Or I should say the rate of change of position is the velocity. So for this fixed triangle, let's figure out what the hypotenuse should be. So the first thing is we take 40 squared plus 96 squared. That's going to be equal to our hypotenuse here squared. This comes from the Pythagorean theorem. Okay, this is a right angle. Towers stand at right angles perpendicular to the earth. So this ends up being, h ends up being 104, I think, meters. Let me double check that. I'm just going to do it on the calculator because I'm feeling lazy. And yeah, it's 104. So h is 104. So this is all on the like fixed instantaneous triangle there. Okay. The next thing that we need to do is we need to figure out, we need to set up some equation and do the implicit differentiation here. So I need this relationship to include theta and to include the rate of change of position with respect to time, so the velocity, okay? So what I'm going to do is I have this and I have this. So I'm going to use tangent. I'm going to say the tangent of theta is equal to, let's call the distance x here. At a particular instant, it's going to equal 96 meters, but this distance from the base of the tower to the car is going to be x. It's going to change over time, and we're actually interested in the rate of change. That's going to give us this value here. So we're going to say that the tangent of theta is x over 40. 40 doesn't change. If 40 changes, then the tower is no longer standing. So it's going to be opposite over adjacent, which is x over 40. Now, I want to do an implicit differentiation on this, so I'm just going to solve for x to make it easier. I'll put 40 over here, so it's going to be x equals 40 tan theta. Okay, so we're going to differentiate both sides of this equation with respect to time. So dx dt is equal to 40 secant squared theta d theta dt. So because I'm doing implicit differentiation, I need to keep this d theta dt. Okay. All right, some of these values are known. We are looking for this value, so maybe I'm going to rewrite this and then solve for d theta dt. So this is going to come up here. So we get dx dt, which is equal to 40. Now, secant is equal to 1 over cosine. So this is 40 over cosine squared theta times d theta dt. Now I can solve for d theta dt. I'll multiply by cosine squared, divide by 40. So d theta dt is going to be cosine squared of theta divided by 40. And actually, let's go ahead and keep in mind that this is meters, okay? This is meters times dx dt, dx dt. Okay. Now, everything on this side is a known value. The cosine of theta is going to give us a ratio of sides of this triangle. So we can actually just plug that in here. So here's theta, adjacent over hypotenuse is going to be 40 over 104 squared over 40 meters times negative 10, that's our dx dt, meters per second. Okay, meters cancel. And then I'm just gonna plug this into the calculator because I'm feeling lazy. So this is negative 400 divided by 104 squared. Okay, so this ends up being approximately, oh, you can't see that because I've got the picture in picture. See, when I did this before, actually maybe you can't see any of this. When I did this before, I was like worried about being able to see this one particular thing, and then I didn't realize you couldn't see any of the thing. So I was super bummed when I realized what I had done. But what can you do? Can't always win. All right, so here we go. So bringing this up here, this is approximately equal to negative 0.03698, 0.03698 radians per second. And actually, maybe we can just, this will be, boom, that'll go there. And actually, let's make this, one of these will cancel with that. So this is going to be equal to 40, negative 400 over 104 squared, which gives us 2 times 52 is this? Okay, so this is 20 times 20, which is 5 squared times 4 squared, which is 2 to the 2 squared, which is 2 to the 4. And then, let me make sure that's right. Yeah, and then 104 squared is going to be 2 times 52, which is 2 squared times 26, which is 2 cubed times 13 squared, so that becomes 2 to the 6 times 13 squared. So this is going to be 2. And so we are left with, let me get rid of some of this stuff. I'll give you the exact value. Negative 25 over 69 times 4, 676. Okay, let me check it. Yeah, okay. This is the exact value. Okay, so yeah, sorry about that. Hopefully that helps. And if it does, please subscribe, like, comment, all those things. Help me become a YouTube math star, if such a thing ever existed. All right, see y'all.